Stop bickering, children.
Single atom.
You're right. Yes, you are. You are right. That makes perfect sense. You just need to understand.
All right. So what we're going to talk about today is sort of an introduction to chemistry and talk about some basic definitions. And then tomorrow we'll really start talking about the periodic table and what it means and what all those numbers represent. I was just joking about your quiz. You're not going to have to write out the periodic table. You're not even going to have to memorize element names or anything like that. You're going to have to be able to use the periodic table to figure out a bunch of different things. All right, so to start off, let's talk about this difference between changes to matter. So in chemistry, we're talking about matter, sort of the stuff that makes up all the physical materials around us. Everything in the universe is either matter or energy. So matter can be changed, and there's two categories here: physical changes to matter and chemical changes. And so physical changes to matter are a change when there's actually no new material is formed. You have the same substances after the change that you did before the change. So examples would be an ice cube melting. That is a physical change. Ice is water, H2O. Liquid water is H2O. You don't have any new substances formed. It may look different. Some of the behavior, the properties may be slightly different, but it's still water. The other thing we often say is that physical changes are reversible. You could take that liquid water and freeze it again, and you have solid water. If I take a glass and it shatters, can I create any new substance in breaking that glass? No. That is a physical change. Yeah, technically, not really, but yeah, so saying that is reversible, I don't love that part of the definition really. Because again, yes, you can never get this glass exactly the same way, okay? But you're not creating any new substances. That's the most important part. In a chemical change, there are differences in what's produced afterwards. New substances are formed in a chemical reaction. And they are usually irreversible. So if you have a piece of iron that's rusting, okay, the iron is actually changing into a new substance. The atoms are being rearranged into a new pattern, and you're forming a new substance. Burning anything is a chemical change. Again, because you're taking a substance and you're rearranging those atoms into a different form. So there are often some signs that we look for if we're trying to identify whether a physical or a chemical change is taking place. Some clues that it's been a physical reaction, just a change in phase. Boiling water, that is a physical change. We have different words for them, but steam and water and ice are all the same substance. Melting a block of gold, that would be a physical change. It's still gold. Dissolving salt in water, that is a physical change. It's still sodium chloride and H2O. We're not creating any new substances. We're just mixing them in a certain way. Changes in size, like I said, shattering the glass, ripping up a piece of paper. Those are just physical changes. Chemical changes are often indicated by things like a change in color. When we added iodine to the starch solution and changed color, that was because a chemical reaction had taken place. The formation of bubbles often indicates a chemical reaction. Smoke being released is an indication of a chemical reaction. So let's look at some examples. Alex, burning a piece of paper, what kind of change would you say that is?
Chemical.
It's a chemical change. Olivia, how about crushing a soda can?
Physical.
Physical change. Lighting magnesium, Brian.
Chemical.
It's a chemical change. So how about mixing vinegar and baking soda?
Physical.
You ever done that? Anyone ever done that? Physical or chemical change? Jake? Yeah, it releases bubbles, right? There's a chemical reaction taking place. The snow melting, Taylor?
Chemical.
No, that's just a physical change, because it's still water, like snow is water. As it melts, it turns into liquid water. Fireworks going off, Grace?
Physical.
Nope. When they explode into different colors and so forth, that's a chemical change.
But like, aren't they going up with the same?
You have to light fire. With fire.
The same one.
Fire. With fire.
With, anytime you have fire, it's
Change.
something burning, exploding, that's a chemical change. Frying an egg, bean,
Chemical.
chemical change. Digesting food in your stomach, creating,
Physical.
no? Because like, Pop-Tarts in your stomach, are they still Pop-Tarts? There's some different molecules afterwards. That's a chemical change. How about chewing your food?
That's
That's physical.
Yeah.
Mixing green and red marbles? Katie? Physical? Aiden, how about boiling a pot of water?
Physical.
That's physical change.
Like, when you boil water, it creates bubbles, so it's not clear.
Yeah, good point. That's why sometimes those aren't perfect. Yeah, it does create bubbles. Those are convection currents, really. But it's still the real thing is still have water at the end. Steam is the water.
I have a question about the matter.
Yep.
Would glass be considered an element?
No.
Made out of steel.
It looks simple.
It's a compound. All right. So we have some definitions we need to understand as we start this unit. These are important. So an atom. An atom, we say, is the building blocks of matter. So an atom is basically made of even smaller parts that we call subatomic particles. And this includes protons, neutrons, and electrons, which we'll be talking about in a minute. Element, as we talked about, these are pure substances that cannot be separated into any other materials. Such as gold. What's the smallest amount of gold you could possibly have? Dean?
One atom.
One single atom of gold. compound, on the other hand, are when you have one, two, or more elements bonded together, forming a unit. So what are some compounds we have talked about? Emma?
Steel.
Yeah, steel is an alloy. It's a little different. Priscilla? Water. Carbon dioxide, glucose. All those things are compounds. They're made of two or more elements. What is the smallest amount of carbon dioxide you can have? Ready?
One atom.
No, because an atom is pure.
Oh.
Jake?
An atom of oxygen and another atom of what's the other one?
Of carbon dioxide?
Yeah. There's
Heat.
two to make it up.
Yeah, and we have a name for that. One atom of carbon bonded to two atoms of oxygen is called a, a molecule of carbon dioxide. A molecule is the smallest part of a compound that is still that same compound, still has the same properties. So we could have a single carbon dioxide molecule, and that would be a carbon bonded to two oxygens. And it's still carbon dioxide, still has all the properties. Could we break it down further? Yes, but it would no longer be carbon dioxide. It would be carbon and oxygen. So if we sort of put all this together, hydrogen and oxygen are what? It's the term we would use for those things. Dean?
Elements.
They're elements. This goes along with what Jake was just saying. So if I have two blank of hydrogen, what do I call the units of hydrogen? If I had two, Grace? No? Go ahead again, Grace.
When, two molecules.
No? Can molecule, hydrogen, Aiden? Atoms. So if I have two atoms of hydrogen and one atom of oxygen, they combine, they form one blank of the blank water. What do they form? Right?
They form a compound.
Okay, but one blank of the compound water. What do we call one? Katie? One molecule of the compound water. Okay, so let's look at atoms. So if we're talking about atoms, an atom is actually made of other parts. Even though it's sort of the smallest basic unit of matter, it's made of smaller units. We call them subatomic particles. There's three types of subatomic particles that are found in atoms. And an atom, you know, we often might see them pictured like this. There's a central part, a core, and then there's some subatomic particles around the outside of that core. The core we call the nucleus. It really has no relationship whatsoever with the nucleus of a cell. Okay, so you can sort of separate those two things in your mind. Okay? But in the nucleus of an atom, the central core area, there's two types of subatomic particles. One type is called a proton. And these subatomic particles, they may have an electrical charge on them, or they may not. Protons are subatomic particles with a positive charge. They have a positive electrical charge. Also, in the core of the atom, in the nucleus, is another subatomic particle called neutrons. What do you think about their charge? No?
They have neutral and no charge.
Yeah, they're called neutrons because they have no charge. They're neutral. They're electrically neutral. So those are in the nucleus. And then around the nucleus, in various orbits, is the last subatomic particle called the electron. And the electron has a charge. What is it, Grady?
Negative
It
charge.
has a negative electrical charge. So if I look here, this is a drawing that's depicting a hydrogen atom, the simplest element that we have. Hydrogen atom has one proton in the nucleus, one neutron in the nucleus, and then a single electron around the outside. Each element on the periodic table has a different number of protons in its nucleus. That's what makes the elements different from each other. It's one of the things. Now, it's sort of hard to conceptualize this, but atoms are really mostly empty space. So we have the nucleus with the protons and the neutrons, and then you have the electrons on the outside, but there is a huge space in between them. Now when we draw it here, it looks like the electrons are very close to the nucleus. That's just so we can fit it on the paper. In reality, if we're paying attention to the actual scale of these things, okay, if there were a marble at the 50-yard line of the Syracuse Carrier Dome, okay, the electrons would be all the way at the outside of the dome. And the nucleus would be a marble at the 50-yard line. So think about it. If you had a marble on the 50-yard line at the dome, electrons would be all the way at the outer edges of that dome. So huge amounts of empty space exist within an atom. Even though, we see this desk as solid, the vast majority of its volume is taken up by empty space. Okay. So we'll just finish up by talking about Mendeleev. So tomorrow you'll be getting a periodic table. You have one in your agenda as well, and there's a couple smaller ones in your notes. But the periodic table is, as many of you were saying at the beginning of class, it's a list of all of the known elements. And the periodic table lists all the elements, their symbols, and some information about each of them. The periodic table, as we know it, sort of has its roots back with a Russian scientist, Dmitry Mendeleev, in the middle of the 1800s, was working on sort of coming up with a system to classify the known elements. At this time, there were 56 known elements. And today, there's about double that. But during this time, scientists started to isolate things like oxygen and carbon and nitrogen and identify them, study their properties and so forth. And so Mendeleev started to make this periodic table with the elements he knew about. So, lithium, boron, carbon, nitrogen, oxygen, fluorine, and various other elements. And he put them together in a certain way. First off, their mass increases as we go left to right through the periodic table. That's how he ordered them. And he put them in a way so that the elements in one column all had similar properties to one another. Everything in this group, lithium, potassium, sodium, they have similar properties. They behave in similar ways. And so you have this repeating pattern. That's why it's called a periodic table. One interesting thing is that along the way, okay, there are some elements that Mendeleev thought should exist, but nobody had found before. And he left gaps in his periodic table, okay, to fit those. Okay? For example, there was an element here, okay, that Mendeleev predicted should be similar to tin and some other compounds, but he didn't know what it was. It was later discovered, and it fit right there in the periodic table. So Mendeleev predicted the existence of elements that no one had ever isolated before, based on their behavior and based on how he set up his periodic table. So this allowed scientists to sort of start to come up with a systematic way to understand the various elements. Tomorrow we'll talk a little bit more about how we use the periodic table and what the numbers on it represent.